Okay, let's have a look at one more Alkenes question. 2019 paper 2. What have we got? We've got double bond, we've got electrophilic addition, cross double bond, using BR this time instead of HBr. Fine, you've got a cyclic compound, so it's not a straight chain, but there's still a carbon-to-carbon double bond in there. So the electrons will come from the carbon-to-carbon double bond. If it were HBr, they would attack bond to the H of the HBr, but it's BR, so they bond to one of the two BRs. The double bond's obviously broken, yeah, and the BR will join onto one of the two carbons where the double bond has been. You can do it either way round, with the BR on the top carbon and the plus on the bottom, or the other way round, doesn't matter. But one of the two carbons where there's been a double bond has now got a BR, and the other one is a secondary carbon cation with a plus on it. The BR that's broken off, of course, is got a minus charge, so the electrons move onto it, and it's got a lone pair of electrons. The lone pair of electrons attacks the carbon plus and bonds onto it. And so you're going to end up with hexane 1,2 dibromohexane, as shown in the picture. Let's have a look at this one then. We've got a polymer in a golf ball. Okay, we have a look at it. Let's have a look where the carbon to carbon chain is right down the middle of the polymer. So you can see where it is, where the two bonds are going left and right, where the chain would repeat itself. So we look at that section there where we've got carbon to carbon single bond and a bond going either side. We don't draw the bonds going either side if we're doing a monomer, because it's not made this polymer yet. And you put a double bond between those two carbons. I'm drawing it at the right-hand side of the screen, where the carbon-to-carbon double bond, where the carbon-to-carbon single bond and the two bonds left and right have been formed when it's made the polymer. And when the double bond is broken to make those single bonds in a long chain polymer. How do I do that as a skeletal formula then? Well, I replace the carbons with dots or corners. I do it as a zigzag sort of shape. So we don't do it in a straight line, we do it as a sort of zigzag shape so we can see where the carbons are on the corners, and the zigzag shape represents the shape of a carbon chain, which isn't straight anyway. So, and then we put the two double bonds in positions at carbon number 1 and carbon number 3. What am I going to name it? Well, it's bute something because there's 4 carbons. Butene. Butene, it should be butene. But it's got 2 enes, it's got 2 double bonds. So butadiene it would be. Butadiene, and the double bonds are at carbon number 1 and carbon number 3. So in the mark schemes it's called it buta-1,3-diene. I think really bute-1,3-diene would be a better name for it, and would certainly get you the mark bute-1,3-diene, because it's come from butene, but the di has been added to give butadiene, and then the 1 and the 3 come before the diene to tell you where the double bonds are. I think the best name is actually bute-1,3-diene. That's a better answer than the mark scheme. The second polymer in the mixture has a repeating unit with the structure shown. The third polymer is a stereoisomer. So you've got no fixed rotation about that double bond. So the positions of the groups in space are fixed. They're in fixed positions in space. That's part of the definition of a stereoisomer, or a geometric isomer, as that is, where you've got a Z isomer. Z isomer where the two groups are on the same side, the according to Kahn-Ingold pre-log rules, where the two groups left and right with the highest atomic number of an atom joined is highlighted or takes priority. The two groups left and right are on the same side that take priority, and therefore that is a Z isomer on the top, and then you can draw the E isomer. So those are geometric isomers, a form of stereoisomer, and you've got Z and E, or you could call it cis and trans if you wanted to, but they are geometric isomers, a form of stereoisomers, and stereoisomers, and remember, is where you've got same molecular formula, same structural formula, but different positions of atoms in space. It comes about because there's no free rotation about the carbon-to-carbon double bond, so that fixes the positions of atoms in space. Why the golf balls don't biodegrade? Because you'd have to break carbon-to-carbon bonds, and they're too strong.